All right, everybody, stay with me here. We're going to fast forward through 1.5 Part A, parametric relationships. We're going to talk about parametric relationships tomorrow in class. So turn the page over and find example B. I want to spend this video talking about inverse relationships. So let's begin with a thought about y equals x squared. What do we know about y equals x squared? Well, algebraically, y equals x squared. Graphically, it's parabolic with its vertex on the origin. Numerically, it's formed from this input-output table. If I plug in -2, I'm going to get out 4. If I plug in -1, I'm going to get out 1. If I plug in 0, I'm going to get out 0. If I plug in 1, I'm going to get out 1. If I plug in 2, I'm going to get out 4. Now, the inverse of that, what's the opposite of a square function? The opposite is the square root. Remember that when you square root something, you have a positive and a negative root, or a principal and a negative root. So the inverse of y equals x squared is technically y equals plus or minus the square root of x. What this looks like graphically is the positive square root, the negative square root, those join together to form that sideways parabolic shape opening to the right. Numerically, what is this going to look like? Well, the cool thing about inverses, remember, is that your inputs become the outputs. -1, jump the gun there. 0, 1, and 2. Your inputs become the outputs, and then your outputs become the inputs. So 4, 1, 0, 1, and 4. Let's find those points on this graph. Let's call this 1, we'll call this 4. So I'm going to go over 4 up 2, over 4 down 2, over 1 up 1, over 1 down 1, over 0 up 0. So see how that works? My inputs become the outputs, and the outputs become my inputs. So the cool thing about functions and their inverses, if a function has an inverse that will also be a function, it will pass the vertical or the horizontal line test. So the vertical line test tells us whether or not a function is a function, tells us whether or not a relationship is a function. Whoa, where'd my picture go? The horizontal line test is going to tell us something important about the inverse. So the vertical line test determines whether or not a relationship is a function. The horizontal line test tells us whether or not a function's inverse is also a function. All right, so let's take these two for example. So I'm going to start with just a vertical line, some arbitrary vertical line. If I swipe it through this function, it passes through the parabola at only 1 point. Therefore, this is a function. One input gives me one unique output. But the inverse of that function is not a function because look it doesn't pass the vertical line test. Every time I swipe through this shape, I cross through at 2 points. Or in other words, one unique input gives me 2 different outputs. So that's the vertical line test. Now let's take a look at the horizontal line test. So here's some horizontal line. The horizontal line test says that if you can swipe a horizontal line through your function and only hit function once, then you are looking at a function that will have an inverse that is also a function. Now, this function doesn't pass the horizontal line test, and that was one way that we would have known that the inverse would not be a function. Okay, so if I kind of just blew your mind there, I want you to rewind a few seconds, listen to that again. Horizontal line test, what's it for? It's for determining if a function is going to have an inverse that will also be a function. All right, so now we've got about half of a page left. What I'd like you to do is take and just divide this into half. Divide it in half. And then we're going to work 2 examples. Over here on the left, let's take a look at the function f of x is equal to x minus 3 divided by 2, like so. Well, this is going to be linear, nothing crazy going on there. It's going to be unbounded. So since it's unbounded, the domain will be from -infinity to +infinity. And since there's nothing funky happening, the range will also be -infinity to positive. Well, that's why it's unbounded, because the range is -infinity to +infinity. Okay, so how do we find an inverse function? Well, the first thing we have to do is remember that f of x is a fancy name for y. Then we do a whole switcheroo. We replace the x's with y's and the y's with x's, and we solve for y. We might have touched on this right before we went into quarantine in Algebra 2. I don't remember how far we got last spring, but anyway, switcheroo, solve for y. So I'm just doing a lot of this mentally. Now, the last step is kind of the most important step. It's where you rename a function as an inverse function. 2x plus 3 is my inverse function. F to the negative 1 is industry standard notation for inverse function. Well, what did we end up with? We ended up with another linear function. I can plug anything I want into this function. So the domain is from negative infinity to positive infinity. I can get out anything negative infinity to positive infinity. This linear relationship is going to be unbounded. Well, this isn't terribly exciting. This isn't a terribly exciting example. What I'm trying to prove to you is that the domain will become the range, and the range becomes the domain in these inverse functions. Let's take a look at a little bit more exciting of an example. In example B over here on the right-hand side, let's take a look at the function g of x. Let's say that g of x is equal to the square root of x plus 5. Well, before we get going, let's talk domain and range. I know that I cannot have a negative number underneath the square root. Because of that, x plus 5 needs to be greater than or equal to 0. When I solve for x needs to be greater than or equal to negative 5, making my domain everything from negative 5 to infinity. So think about that. I can't have anything less than 0 underneath that square root symbol. What's the first thing that's going to give me 0? Negative 5. And then anything less than negative 5 is going to result in a negative number underneath there. And then along those same lines, what does that imply about my range? It means that the smallest number I'm going to get out of this function is 0. So all of my possible outputs will be from 0 to infinity. All right, let's do the fun work. Let's remember that g of x is a fancy name for y. Let's do a switcheroo. Let's solve for y. I just squared both sides to undo the square root. X squared minus 5 will be equal to y. And then remember to rename. So when I rename, my inverse function will be x squared minus 5. Inverse function is x squared minus 5. Okay, what's this going to look like? Let's think domain and range. Well, I know that this is a parabola just shifted down 5. And because it's a parabola, I'm thinking, all right, my domain is going to be from negative infinity to positive infinity, and then my range would be from negative 5 to positive infinity. How does that compare to what I started with? Well, my domain became my range. That's all cool. But here's where I have an issue. My range did not entirely become my domain. I have a situation where there is inherited domain restrictions. I have an inherited domain restriction. Because there's an inherited domain restriction, I have to go through and I have to back out that negative infinity, and I have to lock it in to 0 to infinity. What that means then is this part doesn't count. The only part of this graph that is like legit, for lack of a better word, is this right-hand section from 0 to infinity. So inherited domain restrictions are a real thing, something we need to be always aware of and always considering when we're working with inverse functions. All right, let's turn the page now and look at one-to-one. So what makes a function one-to-one is when a function passes both the horizontal line test and the vertical line test. So let's do a little yes to this and no to that. So yes, a function that would be one-to-one would be something like f of x is equal to x minus 3 over 2, and f inverse of x, which was, oh gosh, what was it, 2x plus 3. Those are both linear functions that are going to pass both the vertical line test and the horizontal line test. So remember, this was something linear. It's going to pass both the vertical line test and the horizontal line test. So that means that what that's implying then is that the inverse function truly is a function. Okay, so this was a yes. Something that's a no was our function y equals x squared. And then remember, I'm going to not call it y, I'm going to call it f of x so that I can rename its inverse as f inverse. So remember there we got plus or minus the square root of x. That was our inverse function. We started, this was f of x. Let's see, is f of x 1 to 1? The answer is no, because even though it passed the horizontal line test, it did not pass. No, I said that wrong. Yes, it passed the vertical line test, but no, it did not pass the horizontal line test. So what that's implying, therefore, f inverse is not a function. It's not a function. It's also implying something else important that we're going to write down here. And f of x is not 1 to 1. Over here, yes, f of x is 1 to 1, again, because it passed both the vertical and the horizontal line tests. Okay, let's skip down to the inverse reflection principle. And the inverse reflection principle just says that a function at its inverse will be symmetric with respect to the line y equals x. So I know it didn't print very well for you, but if you have a highlighter, why don't you go through and draw in that line y equals x. Remember, this line y equals x is the linear parent or the constant parent y equals x. That's something we talked about a few days ago. And then I'm going to pick up another fun function. I put the fun in functions today. Just kidding. I never put the fun in functions. F of x is equal to x plus 4. Remember, that's like y equals x plus 4. Let's do a whole switcheroo. X is equal to y plus 4. X minus 4 is equal to y. Rename. F inverse of x is equal to x minus 4. Okay, so the reflection principle, the inverse reflection principle to be exact, is just saying that your two functions, as long as they're inverses of each other, 1, 2, 3, 4, 1, 2, 3, 4, up 1 over 1, they will be reflections of each other over the line y equals x. This guy, this inverse, is x minus 4, so I'm going to start at negative 4. 1, 2, 3, 4, still the same slope. And if I were to fold this graph over that yellow horizontal line, y equals x, the two lines, the green line would lie right on top of the blue line and vice versa. I can prove that to you using just some points. That's fun too. For example, what is this? This is 2, 6 over 2 up 1, 2, 3, 4, 5, 6. So because that's the case, you know what else better lie on this graph? 6, 2. 1, 2, 3, 4, 5, 6, 2. Yep, close enough. 6, 2 is also on that graph. Here is the ordered pair over negative 4 up 0. Go over 0 down 4, over 0 down 4. That point's also on the graph. All right, so the last thing I have to say about this are all of the fun facts or all of the reasons why I love inverse functions. So, inverse functions. You need to do the old flipperoo. It's a very technical term. They're reflections over y equals x. Inverse functions, x's become y's and y's become x's. What else do I love? Oh, the other thing I love about inverse functions, the domain will become the range, and the range becomes the domain. And sometimes you inherit restrictions. Sometimes you inherit restrictions. Okay, I think that's all I have to say about that. Tomorrow, we'll talk about parametric functions, which are equally as cool as inverse functions.